It's my privilege to invite John here, have John here to speak today. John Simon is an alumni of Caltech. He was an undergraduate here, physics student, and a soccer player, he tells me. Mainly a soccer player? No, half a soccer player. After leaving Caltech, he went to Harvard and worked with Vladan Vuletic at MIT, and then ultimately actually did his postdoc at Harvard in Marcus Schreiner's lab. After that, he transitioned to the University of Chicago, where he's developed a number of really amazing experiments in studying the formation of quantum matter from light. And this is what he'll tell us about today. So there's a few other things here that I found very interesting in John's biography, which I wanted to point out. So
should I be nervous?
No, no, no. The first is that his interests include quantum optics, quantum materials, to the theory of control, and Brazilian jiu-jitsu. So clearly, and I know that because I'm a Facebook friend and I see a lot of his jiu-jitsu activities. His other interest is cats. So I think that I don't know exactly, how many cats do you have? Several? One?
I have one cat.
Okay, one cat. So, very interesting.
Are you sure
biography.
You're pleased to have me here?
Yeah.
He's trying to say you got something from me, at Harvard.
Yeah. So, without further ado, I will let John tell us about these magical materials that he's been working on. Yeah, take it away, John.
Thanks, Oscar.
Let me set the mood here for your talk. Did I do that right? Okay.
Looks good. All right, I see, and the mic's on too, great. So firstly, it's really a pleasure to be back. I was a Lloydie many years ago. I had not forgotten how amazing the science here is, so I've really enjoyed all the lab tours and interactions. I had forgotten how fragrant the campus is. I don't know if you all live here, so you probably don't notice it, but the next time you go outside, the campus has a really uniquely wonderful citrus smell. So try to appreciate it. So in the next 2 hours? No, oops, too many slides. No, I'm going to tell you about the ongoing work in my group and also in close collaboration with my friend and colleague Dave Schuster, making materials out of light. So before I can tell you about the materials that we made, I thought I'd take a moment to step back and just talk briefly about what, in my mind, it means for something to be a material. So the expression that I like in nice short form is a collection of particles that interact with one another and thereby organize or order. So what I have here is a very simple simulation. Okay? Each of these particles obeys F equals ma. The forces are attractive between the particles at long distances and repulsive at short distances. And I've added just a little bit of friction. Okay? So when you run this simulation, you get a crystal. I didn't impose any crystalline structure, but the point is a very simple set of laws can give you interesting and beautiful emergent behaviors. But you really need all three of these ingredients. So what do I mean a collection of particles? Well, I mean objects with some non-trivial dispersion relation. That is to say, you can apply a force to them, and their velocity changes. They deflect, they speed up, they slow down. We need to be able to make these particles interact with each other. That is to say, they need to apply forces to each other that depends upon their distance apart and orientation. And then we need something to help them organize or order. That is to say, something to take entropy out of the system to prepare some ordered state as opposed to preparing some excited state of the system. So if you want to make a material now out of photons, you run into a couple of challenges. The first one is that forces don't slow down photons. So if I have some massive particle here moving to the right, and I apply a force on it to the left, it slows down and then it eventually moves back to the left, right? If I do the same thing to a photon, it doesn't slow down at all, right? Its momentum decreases. Well, actually, I guess I had the force going in the other direction. I apologize. Its color changes, right? But its speed doesn't change. So this seems like a problem if I'm going to try to make materials out of light. What we'll see is that the solution to this is that we have to go from a linear dispersion, which basically says that when I increase the energy, the group velocity doesn't change, to trapping my photons in some medium that have a non-trivial dispersion. That is to say, there's some non-trivial relationship between the group velocity and the momentum. Okay? So we're going to have to trap our light in some kind of a material to make this happen. OK, that's step one. The second challenge that we're going to run into is that when we bring electrons towards each other, they can collide. If I have a wave moving to the right or a wave moving to the left, the linearity of Maxwell's equation says that when I have both, they just go straight through each other. Right? So what this says is that I need some way to make these photons see one another, collide, interact. Okay? So to get a flavor of how we'll solve that problem, you can look at how electrons collide. Well, electrons don't directly interact with each other. In fact, what happens is if I have two electrons come in, they can exchange a virtual photon and go back out. And the collision is thus mediated by exchanging photons. So I didn't know that Professor Frauci was going to be here today. He taught me quantum field theory 16 years ago now. So there's the Feynman diagram. There you go. So you could imagine trying to just turn this on its head and say I have two photons come in. They can exchange an electron and go back out. But of course, this diagram isn't allowed. Conservation of charge, for example, precludes that. The lowest order diagram one can have, we can convert an electron into two photons and induce collisions in this way. The cross-section for this process to occur for optical photons is about 10 to the negative 56 microns squared. So that is to say, if I have one photon come in, the other photon has to hit an area of about 10 to the negative 56 square microns to see the first photon. Okay? So this is a very unlikely thing. You know, that's much smaller than the wavelength of the photons. It basically doesn't happen. But the essential thing to notice here is that the rate for this process to occur is suppressed by the energy cost of creating these intermediate electrons. Okay? So what we need to do is have our photons be able to create excitations in matter that, instead of being way off resonance, are essentially resonant. Okay? So this is going to be the second ingredient that we'll have to use. But we'll have our light interact with matter, the matter interact amongst itself, and that turn back into light to make the photons collide with each other. Okay, so the final challenge initially looks sort of fundamental. As we make systems more and more quantum, what does that mean? Well, what it means is that we're decoupling them more and more from the environment. Anything that can measure them and collapse the wave function and destroy our entanglement has to go away. Right? But this seems problematic because even for a classical system, if I turn off all the friction, I don't get a crystal anymore. I just get like a horde of bees, a horde of undergrads, I don't know. Cats. Right? My cat is very well behaved. She's nothing like that. Okay, so what we'll need to do is ultimately find a solution to that, and we'll come to what the tricks are there at the end. Okay, so that sort of sets the stage, and I just thought I'd very briefly bring this to something that maybe we're a little more familiar with. Okay? In a solid state material, our electrons interact through a Coulomb interaction, so that gives us our interaction piece. The dispersion of the electrons, well, they have some dispersion in free space, right? They just obey F equals ma. But if you put them into some ionic lattice, that can change their mass. It can give them a more sophisticated dispersion. Okay? And then we can connect this thing to a dilution refrigerator to cool it down and suck the entropy out. Okay? An analogy that many of you are likely familiar with is to replace these interacting electrons with interacting laser-cooled atoms, and to replace the ionic lattice with a lattice of laser beams. Okay? And this lattice of laser beams will produce some band structure, some dispersion for our atoms. So again, the story that I'm going to tell you today is about going a step further to replace the interacting atoms with interacting photons, and to replace this optical lattice with some kind of an extremely low-loss metamaterial structure to make the photons behave as some kind of a massive particle. And so what I hope we'll take away from this at some level is what it really means for something to be a material and what the minimal ingredients are. And also we'll see that there are some sort of interesting material properties that one can engineer for photons that are very difficult to realize for cold atoms or even electrons. Okay, so the two platforms that I want to tell you about, with all of that out of the way, are first bulk gases of optical photons interacting with one another through some laser-cooled atoms and trapped in a magnetic field. And then the second half of the talk will be about microwave photons hopping around in a superconducting lattice and colliding with one another, with interactions mediated by transmon qubits, these things that Oscar works with for quantum computing. And this second story is work in collaboration with Dave Schuster. Okay, so let's hop right in. So the analogy I would like to share is that photons in a multimode optical resonator behave like massive particles in a harmonic trap. So what does that mean? Well, imagine I have two mirrors here, shown in blue, and I'm going to shine light into this cavity off-center. My claim is if you look in the middle of this cavity, the light should bounce back and forth transversely like a massive particle in a harmonic trap. Okay? So let's see if we can understand why that is. The sort of simplest picture you can have for this is just ray tracing. Okay? The light bounces back and forth, and you can see that kind of the tilt of the ray tells you about its momentum, okay, in the transverse plane. And the propagation back and forth along the cavity axis maps this, this tilt into displacements. Okay? And the curvature of these mirrors kind of refocuses us and prevents us from just continuing on forever. That gives us our harmonic trapping. Okay? So this is the simple analogy for what's going on here. There's sort of a more formal Floquet picture for experts who are interested. But it turns out this sort of hand-wavy physical analogy I've given you has a very nice and sort of more concrete realization in the wave picture. So if I look at a quantum harmonic oscillator, we all know that the eigenstates of a quantum harmonic oscillator are Hermite-Gauss in space, and they're uniformly spaced in energy. Okay? If anyone has ever made a gas laser, anyone? Okay, one. Honestly, I haven't even made a gas laser, but if you have, then you know that these things can laze on many different transverse modes. And indeed, these are features of the cavity, not the gas in particular. And the transverse modes of such a cavity are Hermite-Gauss in space and uniformly spaced in energy, which is to say that this hand-wavy picture that I gave you really applies in a very formal physical sense. Okay? So we can look at this one more way. If I inject light into my cavity off-center, I can write the wave function of that photon as a superposition of the lowest transverse mode of the cavity and the first excited transverse mode. Okay? But these two modes are not at the same energy. So sometime later, this plus sign will evolve into a minus sign. And so now my photon is off-center to the left of the cavity axis. Okay? And if this looks familiar to you, it should. This is how coherent states in a quantum harmonic oscillator oscillate back and forth, right? Which is just to say that a photon living in an optical cavity really behaves like a massive particle in a harmonic trap. The picture you should now have in your mind, I have these two cavity mirrors. I have light bouncing back and forth in the longitudinal direction, okay? And I'm thinking, for the experts, of a single longitudinal quantum number here. So the light is delocalized everywhere longitudinally in my cavity and oscillates back and forth transversely like a massive harmonically trapped particle. Okay. So in some sense, this analogy has been explored for very weakly interacting photons. The interactions usually are induced either by hybridizing the photons with excitons, in which case one arrives at exciton polaritons, where people have seen Bose-Einstein condensation and sort of classical fluid dynamics of these photons. And photon condensation, where the photons essentially don't interact with each other at all, but they do thermalize with a dye that's been put inside of the cavity. Okay? So we're going to eventually make our photons very strongly interacting. But the first thing I'd like to do, even before I do that, is ask, is there a way to add a magnetic field to this problem? That is to say, can I make my photons behave as charged particles in a magnetic field that undergo some kind of Lorentz force and exhibit cyclotron dynamics and so forth? And for anyone who does condensed matter physics of exotic materials, you know that applying magnetic fields and seeing how the particles respond to them, the electrons respond, is very important. So we need to do that, particularly if we want to study topological physics here. So the question is, how do we add a magnetic field for the light? Well, there are a number of proposals of ways to do this. In particular, this one from Gil Raphael and colleagues suggests that by hybridizing with electrons in the appropriate way, one can induce topology. What I'd like to suggest is that there's another way that doesn't even require coupling to anything other than mirrors. And the trick is to twist the cavity. So what do I mean by that? Well, to understand that, we need to go back to World War II submarine movies. No, seriously. So when you watch a World War II submarine movie, the submarine captain looks through his periscope, right? And when he wants to look in that direction, he turns the whole periscope around, right? Why is that necessary? Why can't we just rotate the top mirror? Well, the picture is this. Imagine light moving through a periscope. So I'm looking at this tree through my periscope. Okay? If I rotate the top mirror relative to the bottom mirror, the tree comes out rotated. Okay? And so indeed, the rotation angle of this tree just depends upon the twist angle of the periscope. So if one built a cavity consisting of two mirrors like this that are twisted with respect to one another, and then just two more mirrors to close the path, in addition to this harmonic trapping and this mass and all of that other physics that we've talked about, on every round trip through the cavity, the trajectory of the photon gets rotated a little bit. Okay? So effectively what we're doing is turning, okay, we lost something there, but this is close enough. Turning the lab frame into a rotating frame. Okay? Normally, when we talk about working in a rotating frame, we're saying physics takes place in a stationary frame, but I'm rotating around it, right? And then you get fictitious forces. But the story here is that by twisting the cavity out of the plane, On every round trip through this cavity, it's really like the whole world, the inertial frame is rotating. Okay? So we get a Coriolis force for the photons and a centrifugal force that are real forces on the photon. Okay? And this centrifugal force just pushes you out radially, and you can exactly cancel that by adding curvature to your mirrors. Okay? And then what you're left with is a Coriolis force. Okay? And if you just have this Coriolis force, well, a Coriolis force is omega cross p, which is basically proportional to v cross b. So we've now generated a Lorentz force on our photons just by taking our cavity and twisting it out of the plane. Okay? So we can do this in practice. This experimental setup actually initially is quite simple. It's just 4 super polished mirrors of the variety that Jeff Kimball pioneered for cavity quantum electrodynamics, stuffed into a 3D printed plastic structure that keeps them properly pointed at each other to give us this twisted geometry. And when we look at the modes of this cavity, the modes of the cavity, it turns out, are now these Laguerre-Gauss ring modes, okay, which are exactly the eigenmodes here of the lowest Landau level. Okay? So what I'm showing you here is as I vary the length of the cavity away from some degeneracy point, and what that degeneracy point is as I change the length, I'm sort of very subtly changing the trapping. And I'm trying to find an amount of trapping where the harmonic confinement exactly cancels this centrifugal force, okay, such that all I'm left with is a Coriolis force, which gives me a bunch of degenerate modes forming a Landau level. Okay? So these modes of the cavity, and this is real data, become degenerate here. And we can, in fact, zoom in further, and we can see that we can make these modes degenerate to better than a megahertz. So why is this number important? Well, the next thing I would like to do is add interactions to this story. And now we're going into the regime of quantum optics. Okay? And what we would like to have happen is the interactions make the photons prefer some superposition of these modes that keeps them as far away from each other as possible. Okay? And it turns out that Bob Laughlin in the 80s made a suggestion as to what that state should be. It's called a Laughlin state. It's a topologically ordered phase of light in this case, or electrons in his case. And the point is that the interactions between the particles need to be larger than any disorder in your system so that the ordering is determined entirely by the interactions. Okay? And so we're going to need interactions which are large sort of compared to a megahertz. Okay. So because I'm at Caltech, I've put this slide in. It's rather technical, so I'll zip through it very quickly. There is a way to measure the Churn number, which is this sort of indication that your system is topological, okay? Even in a system where that doesn't have periodicity, okay? And it's buried in a supplement of one of Alexei Kitaev's papers. But it's actually an extremely powerful method of characterizing topology in continuum or lattice systems, actually. And so we've actually managed to make a measurement of this quantity essentially by measuring projectors onto Landau levels and onto regions. So just very briefly, what we see is that the Churn number for the experts converges when we look at regions that are a couple of magnetic lengths across. Okay, aside over. How do we make photons interact? Because the next thing that we need to make a material is interactions between our particles. So how do we make them interact? Well, as I said before, the key is to make the photons interact with matter and make sure that the matter particles interact with each other. Okay? So the game here is to send our light into an atomic medium, okay? And create a situation where the light propagates through the medium. This first photon, this black photon, propagates through the medium very slowly. So does everyone know what electromagnetically induced transparency is? Okay, we've got for 5 people who know. Okay. Yes, Manuel knows too. That's not enough. Okay. So one can make light propagate very slowly. Why does light always propagates at the speed of light, John? What are you talking about, make light propagate slowly? I agree with you completely. Light does always propagate at the speed of light. So how are we slowing it down? Well, the point is, if you have light which is repeatedly absorbed and re-emitted by a medium, it's not moving while it's in atomic excitation in the medium. Okay? And so this idea of electromagnetically induced transparency, slow light, basically says my light enters my medium and is repeatedly absorbed by my atoms and re-emitted. Okay? But if it spends most of its time as an atomic excitation, the light will move through the medium very slowly. Okay? And so what we do is we create a situation where our light comes into the medium and gets excited up to it excites an atom in the medium up to what's called a Rydberg state. And these Rydberg states are very, very long-lived. Rydberg state means that the principal quantum number of the electronic orbital is high, in our case 100 or 110. Okay? So for a ground state atom, the orbital size is typically on the order of a nanometer. Okay? For these Rydberg atoms, the orbital size is on the order of a couple of microns. Okay? So these large orbitals give us 2 benefits. One is that they're very, very long-lived, so that the light can spend a lot of time as an atomic excitation as compared to as a photon. Okay? So the light can go through the medium very, very slowly. The other benefit, and this is the more interesting thing, is that when I send a second photon into the medium, if it tries to excite an electron up to this Rydberg state, these electrons can see each other from a micron or 2 apart, right? Because the electronic orbitals are so huge, even if the 2 atoms that did the absorbing are a couple microns apart, we can actually see effects up to 10 or 20 microns. These electrons repel each other, okay? And so what this means in practice is that once a photon has gone in here and been absorbed by this medium, a second photon can't be absorbed near the first one. Why? Because this Rydberg state has been shifted off to infinity. Okay? And now you see why this has to be a Rydberg electron and why we don't see this kind of physics every day in our lives. Right? If this is a low-lying atomic excited state, these atoms have to be within a few nanometers of each other to interact. And the photons are big, so the probability that both photons are absorbed by objects within a few nanometers of each other is very, very small. Okay? So why don't we see these Rydberg absorptions of light in the air? Well, the absorption cross-section is small there, for one thing, and there's a trick with this second laser that I've ignored for that. So, and we'll just ignore that piece. But the other piece that's really tricky is that these Rydberg atoms are very, very close to the ionization threshold. So they're very delicate. So getting hit by any air particles tears them apart. Okay? And so the basic point is that this atomic medium, in our case rubidium atoms, has to be kept extremely far away from everything in the world. It has to be held in a vacuum chamber. Otherwise, these Rydberg states aren't stable. Okay, so in practice, what happens? We take a laser-cooled gas of rubidium atoms. We transport it into a cavity. So this is the mode of this cavity. We slice this cloud down to about 10 microns thick, and then we look for strong interactions between the photons. So how does this happen in practice? Well, we send a laser beam at the cavity, and we see what comes out the other side. And the point is, this cavity can easily absorb a first photon, but once one photon has come in, this sort of collision mechanism between the photons prevents a second one from going in, okay, until the first one leaves. And then a second one can enter. And so what this means is if we look at light coming out of the cavity, there should be some maximum rate at which photons can come out. The more strongly we drive the system, the less light fractionally we should get out on this central peak. But more broadly, and this is where things get interesting, if you look at the transmission through the cavity, the photons should come out in single file, We should never see two at the same time. And so if you look at the probability of a second photon coming out, given that one just left, you see that that probability is suppressed for some period of time, meaning the system only holds one photon at a time. OK, so that's very nice. But I told you we're going to make some materials here. So what we're going to make now is a topological molecule of light. OK, what do I mean? Well, I want to combine these magnetic fields for photons with photon-photon scattering and see what kind of a state we make. OK? So let's think about what kind of experiments we can do. And so one can imagine, and this is what I've been telling you about to this point, send light into the lowest mode of this cavity. OK? Well, I can put one photon in, but I can't put a second one in. And so what I see on the output is photons coming out in single file. Right? And Jeff Kimball pioneered these experiments in the early 2000s. The really cool thing happens when we try to send light into this L equals 1 state in the cavity. Well, L equals 1 meaning 1 unit of orbital angular momentum in this lowest Landau level for the light. What happens? Well, you might say, I shouldn't be able to put two photons in because they repel each other strongly, right? So there should be a big energy cost to have two photons in the system. But there's a very interesting thing, which is I can conserve energy and angular momentum by taking two photons in the L equals 1 state and having them collide and go to 0 and 2. Okay? And so as a consequence, we now have to ask, is there some superposition, two-particle superposition state, okay, of two photons in this L equals 1 state and one photon in 2 and one photon in 0 that has no interaction energy? Okay? And the answer is yes. In fact, there is. For the experts, the wave function in a first quantized notation looks like this. The statement is, why is this no contact interaction? Well, if the locations of the two particles are the same, if z1 equals z2, the wave function is 0. Okay? And why are these states equivalent to that? Well, these angular momentum states are z to the L times this normalization factor. Okay? And so you can just multiply this out, and you see that I get one term which looks like z1 squared, z2 to the 0, okay? Which is one photon has 2 units of angular momentum, and the other has 0 units of angular momentum. And then I have one term which is z1 to the 0, z2 squared, which is just the symmetrized partner of the other one. And then I have a third term which is z1, z2, okay, which is both of them having 1 unit of angular momentum. So the point is this superposition state actually corresponds to no contact interaction energy. So when I send in light on this L equals 1 mode, what I expect to get out is this Laughlin state of light. Okay? So how do we do this experimentally? This is sort of a neat thing. It's actually a combination of quantum optics and classical optics technologies that have been developed over quite a long period of time. So the game essentially is this. You send in a laser beam, and you give it angular momentum by sending it through a hologram. Okay? Then we send that into this interacting system where these photons, actually, I think I have a better version here. Yeah, so I send that into this interacting system where the photons can collide with each other. And what I expect will come out the other side will be these two photon Laughlin molecules. Okay? Because that's the only thing that was at the energy of my drive laser beam. Right? So the state that comes out has to be at that energy, and so I expect this Laughlin state to come out. Well, I see this very weird-looking correlation function, and I don't want to go too much into that, but the neat thing that one can do is now sort these photons by their orbital. Okay, what orbital are they in? Well, orbital in this case is really how much orbital angular momentum do they have. Okay? And what we see is that we get, on occasion, two photons with the same angular momentum. And it may not be obvious from this data, but if you look here, when we look at correlations between photons with less angular momentum and more, you see about the same amount of time that I get two photons with, in this case, 6 units of angular momentum, I get photons with 3 and 9 units. So this is really this this Laughlin molecule. What I've shown you to this point is that we have an equal superposition of these two states. One needs to measure that phase. And the game for doing that, and this is what my students are doing right now. I had hoped to have the data, but it's not in a form I'm comfortable showing, is that anywhere you look in space, the photons are anti-bunched. OK, so I don't know why this isn't there. OK, great. So I promised you a picture of my cat. Or rather, Oscar promised you a picture of my cat. So this is Emmy. She's named Emmy because when I adopted her, she liked to look at herself in the mirror. And I know that's a discrete symmetry, not a continuous symmetry, but she's a cat, so give her a break. OK, so that's the first story. We can make topological molecules out of light. The second story I wanted to tell you is about making crystalline phases of light and entropy management. So let's go back to where we started. We want to have some kind of a material system where we make photons behave like particles that interact with each other in order. Okay? And what we said was there's a fundamental challenge for assembling a large material, because what you normally want to do to make a material is have particles with these properties and then cool it down, right? But the way you cool it down is by having something that you can dump energy into. That thing that you dump energy into is sort of continuously measuring your system. So if you get rid of that to allow your system to be more quantum, then you get the angry bees. Okay? So what we need to do to make something quantum in the presence of some cooling is have only local cooling that we can eventually turn off. So what should you have in mind here? Now I'm going to show you a little classical animation where there's no damping anywhere but right here. And it's sped up because it takes a while. But the point is that even if I just have dissipation in this small region, as long as the system thermalizes across the whole thing, that is to say, as long as energy can propagate from the outside to the inside, dissipation here will cool the whole system eventually. Okay? And so the story is I'm measuring often here. I have a lot of damping here, but I'll have very little damping out there, and so I can support some kind of interesting quantum state out there. Okay? So that brings us to our second story, which is how does one explore that physics in some kind of a synthetic material platform? And we decided that making materials out of microwave photons was actually the best way to do this. So that's what I want to tell you about now. So first I'm going to tell you about the model, and then I'll tell you about how we realize it experimentally. So what you should have in mind is I've got a bunch of little buckets, and particles can tunnel from one bucket to another. But if they're in the same bucket, I pay some interaction energy cost U, which is, in this case, going to be large compared to their tunneling rate. Okay? So this is what's called a Hubbard model. It's a paradigmatic model for materials. All right? So the question is, how do we stabilize a system like this in the many-body ground state? So what I would like you to imagine is that I have this special object over here that always has one photon in it, or one particle in it. Okay? If anything takes its particle away, it immediately refills itself. Okay? And if you ever give it two particles, it just takes the second one and throws it in the trash. Okay? So what happens if I couple that to my quantum system here? Well, the point is, the first particle tunnels into the system, and this thing refills itself. But this particle now cannot tunnel into my quantum many-body system because it would have to pay this interaction energy cost U, which is, as I said, large compared to the tunneling rates. Okay, so this particle can't enter the system until the next one, the second particle tunnels over by a site, and then this particle can tunnel in and the thing refills itself. and the system fills itself up in this way. So the question is, how do we realize all of these ingredients to explore this sort of dissipative preparation of a many-body state? Okay? So there were all kinds of ideas about how one might go about doing this. People had all kinds of pictures of what such a device might look like. I would say our ideas are most similar to some ideas from Andrew Houck's group. But what I thought I would do in the last couple of minutes is just, I have 50 minutes, yes? Total? Not 50 minutes more? Good. All right. Give you a flavor of how this works. So the first ingredient we need is our bucket that can hold photons. Okay? So what's a good bucket for holding photons? An LC circuit, right? I have an inductor and a capacitor. And if you quantize this object, it has some resonant frequency. And each photon that I put into this system has to have that energy of 1 over 2 pi root LC times h. Okay? So this thing holds photons just of that frequency. So this is a nice object. But the problem is, what I told you is that the photons need to collide in my bucket. Right? I need to pay some interaction energy to have 2 photons in the bucket. So the key is to replace this inductor with something called a Josephson junction. Okay? And the story is that this Josephson junction is an inductor whose inductance depends on how much current is flowing through the junction. Okay? So this is a very neat thing, because if this dependence of the inductance on the current is strong enough, okay, one can easily have a situation where the first photon that this cavity or this resonator holds has to be at 4.5 gigahertz, but the second one has to be at 4.2 gigahertz. Okay, so that's actually a very an attractive interaction between our photons of 300 megahertz. Okay, and so the requirement here is that my photon live a very long time compared to that interaction energy. Okay, so that I can effectively have many collisions between the photons within their lifetimes. Okay? And before we even move forward, I think there's a very important point to make here, which is that this 3-level system, where this 3rd level is not separated by the same as the first 2 levels, is the exact thing that you need to make a quantum computer. Why is that? Well, the basic point is that a quantum computer, you would like to be able to maintain superpositions in a 2-level system, right? If I have just this LC circuit, there's no way to address just these 2 levels. I shouldn't say there's no way. It's more difficult to address just these 2 levels. The key to addressing just these 2 levels in this LC circuit is to couple it to a transmon or to a Josephson junction, right? So fundamentally, you need an object like this. Okay? And so the point is, these tools have been developed specifically by my collaborator, Dave Schuster. He was, I guess, the first graduate student doing this science at Yale a decade and a half ago. And now there are fantastic people using these things for all kinds of awesome science. I spent some time with Oscar in the last 2 days chatting with him about all the cool stuff they're doing with them. But the basic statement is, these devices were developed for making quantum computers, and fundamentally you need more or less the same ingredients to make a quantum material, that is to say, a material where entanglement is pervasive and determines material properties, that you need to make a quantum computer, which is to say a computer where entanglement is pervasive and impacts your calculations. Okay? So great. So I've told you how to make these the lattice site where the photons interact with each other. How do I induce tunneling between one of these lattice sites and another lattice site? A capacitor. So that piece of the story is actually very easy, right? This is like taking two mass spring systems and coupling them together with another spring. Okay? And the point is, I can get any amount of tunneling that I want just by changing that capacitor. Okay? So in our case, we work with about 10 megahertz of tunneling. okay? And an interaction energy between the photons of 300 megahertz. So the way you should think about this is if I put a photon over here, it tunnels back and forth in about 100 nanoseconds, okay? And if I have two photons in the same lattice site, okay, I will acquire 2 pi of phase more than having one on each side in a time of about 3 nanoseconds. Okay? Great. And then the last number that we care about is how long do the photons live in one of these lattice sites? Well, they live in total for about 40 microseconds. So 40 microseconds feels like a pretty short time until you realize that they can tunnel in about 100 nanoseconds, which means these photons can, in our system, can tunnel about 400 sites, and they can, in principle, collide about 12,000 times. So this is actually plenty of time to build up lots of entanglement between the particles in this system. Okay? So we've developed this device. This is what it looks like. Each one of these little crosses is a qubit. They're capacitively coupled to each other just by these little gaps between them. You can actually zoom in and see the Josephson junctions here. We can tune the qubits through what's called a flux loop to put them all at exactly the same frequency. Okay? And we can read out the occupation of each one of these lattice sites with single particle resolution and single shot fidelity, okay? Which is to say, we now have this quantum many-body system. I don't know, do you call 8 many? Who says yes? Just me? Okay, so there are, okay, so 4 or 5. The people who actually do the experiments raise their hands. And everyone else is like, yeah, 8 particles is pretty lame. Get out. No, you can stay. It's okay. So the point is, we can build this sort of quantum few body, quantum many body system, see dynamics, and read out each particle, each lattice site's occupation individually. So we'll skip those technical details. The one piece that we're missing is how do we make this magical object that is always happy to supply photons of this particular energy, but can never take them back, but is happy to eat photons of this higher energy. Okay? It turns out that object has a name. It's called a chemical potential. Okay? And so to me, one of the neatest things about this piece of the story, okay, is that we learn about chemical potentials all the time in statistical mechanics, right? But how you realize one in kind of a microscopic sense is a little bit more subtle. Okay, so how do we make this object? Well, we actually know about making a device like this. It's the central ingredient, in a way, of a laser, right? We need to have this object stay in this excited state, and if it ever falls down, be re-excited to that excited state, right? So this is what we call optically pumping in the case of a laser, or generating an inversion in this excited state. So the essential ingredients, okay, you need a third level that you can excite to, okay? And the third level needs to decay really fast, okay? So that we can excite the system from this lowest empty state up to the doubly occupied state, and it'll immediately decay down to this singly occupied state, from which our laser doesn't address it anymore. Okay? So we need to figure out how to make this object. Well, we need 3 levels. What's a good thing to have 3 levels? How about a qubit? And then what we need to do is make this doubly excited level decay faster than the singly excited level. And this is sort of a neat thing, and this is where circuit QED and electrical engineering in general really comes in handy. What we can say is what we want is fast decay of photons of this energy and slow decay of photons of that energy. So what we should do is couple this object, this transmon qubit, to a lossy cavity, or a lossy resonator, that's tuned to that frequency. Okay? That is to say, just an LRC circuit with the appropriate LR and C. Okay? To be at this frequency, but not at that frequency. Okay? And you combine that with a drive that excites you from the empty state to this doubly excited state, and it turns out this gives you that dissipative thermal reservoir chemical potential, if you like. Okay? Just to be clear, in some sense, this is an idea that's not entirely new. Okay? How do people evaporate to Bose-Einstein condensation of cold atoms? Well, the basic statement is that you take two atoms and you let them collide, and you make sure that when you go past a certain energy, the high energy particles fall out of the trap. Okay? You may also have some experience with this from your cup of coffee, right? Because that's called evaporative cooling. In any event, the point is that this is exactly the procedure we're using in our experiments. We inject two photons into the system, right? One goes up to this excited state and is emitted into this lossy channel, and the other one goes into our experimental system. Okay. This is fuzzy because of quantum uncertainty. Okay. Or copy and paste problems, one or the other. So I don't want to go too much into how this object operates, except to show you what happens when we put it into practice. So the point here is that if I excite, so this is my 7-site chain plus 1 thermalizer at the end, okay? And when I turn on this stabilization drive, the system starts out empty, and then you can see this sort of causal wavefront of particles propagating into the system and reflecting off and coming back, and the system then fills up over several microseconds till it has 1 particle in every site. Okay, and so this kind of dissipative stabilization of this crystalline state with 1 photon per lattice site really works. One can also ask, what happens if I take a filled system and kick a particle out? Well, if I don't have this stabilization drive on, I get kind of a quantum random walk of this hole around in my system. Okay? If I turn on the stabilization drive, I start to get the quantum random walk, and then it gets to the stabilizer at this edge of the system and just gets eaten. Okay? And so the point is, I can see the real quantum dynamics away from this dissipative measurement object, but when I get close to it, it quenches the quantum evolution and projects me back into this pure Mott phase. Okay. The next step on this side is to combine this with some topological circuit tools that we've developed to start to explore fractional churn insulators and hopefully eventually anionic physics. This is to say fractionally charged and fractional statistics quasiparticles. And there are, I guess, a variety of other sort of interesting things that one can think about here. I do like my cat, yes. It was going to be funnier if Oscar hadn't mentioned that I liked my cat. Now it's just a little awkward, but not that awkward. You can see her little harness there because she likes to go on walks. I'm that guy at the park. Mm-hmm. So with that note, I think I would like to thank all of you for your attention and my group as a whole, but I think the most important people to highlight here, first and foremost, my collaborator, Dave Schuster. The circuit experiments were done particularly by Alex Ma, who I can't say where he's faculty. I don't know if I can say where he's faculty yet. He's faculty somewhere now. And Brendan Saxberg, and the photon experiment, the optical photon experiments were done primarily by Logan Clark, who will be on the job market next year, and Nathan Shine, who's on the postdoc market now. So thank you for your attention.
Okay, so we have some time for John or Emmy, whichever. Alp?
In the pair generation process, would you be able to get the similar effects with, for instance, a large cavity with a small FSR and using different longitudinal modes?
For the microwave stuff?
No, sorry, for the optical photonic molecule, like a rainbow, I guess you call it the Lachman state. It kind of looks like frequency home generation.
Yeah, so it looks a little bit like a parametric down converter,
Yeah.
right? The challenge is that in a parametric down converter, you have mostly your coherent beam and occasionally pairs, right? If you want to build a topologically ordered state, you have to have an equal mixture of the two. And I know for a 2-photon kind of molecular state, it may not look particularly different, but if you want to build up to a bigger ordered state, the collisions have to be deterministic with high probability. And so you could see collisions between longitudinal modes, but they wouldn't have the sort of spatial characteristics required for the topological physics.
Please.
I want to take an issue with your the first half of your talk.
Okay.
The Lachman state is interesting because it's a many-body wave function.
Mm-hmm.
You can describe 10 to the 10
Mm-hmm.
particles. But when it comes to two particles, it's basically something very trivial, which is what you have.
I agree.
So I think the Lachman state is stretching.
So two things. One, I agree with you completely. Two, I called it a Laughlin molecule for a reason. But to me, there are sort of a number of interesting things here. One is, once you've got the ingredients to make two, you can use those ingredients with this dissipative preparation and these sorts of things to make Laughlin states of 10 or 20 or 30. And it looks like you can see anionic physics with as few as even 5 or 10 particles. So to me, a piece of the really fascinating challenge is, how many particles do I need to see fractional statistics, right? I mean, I don't think anyone's actually ever made a Laughlin state of 10 to the 23 electrons. That's an awful lot. But you know, does it have to be 100,000 or 1 million? Or can I see the fractional statistics with 10 or 20, right? And I think, at least for me, that those are the fundamental and sort of interesting challenges. But I agree, you know, with two, it's a Laughlin atom, or maybe a Laughlin molecule.
Fair enough. I mean, Laughlin came to a state by solving a 3-body problem.
Yes, yes.
Can I just ask a follow-up question on that? So you also have the other, I mean, related between the first half and the second half of your talk and things that we talked about, you know, yesterday. How do you, in your Rydberg atom experiment, you also don't have yet a chemical potential that protects you against particle number loss, right? So you lose photons. Can you comment on what the lifetime is currently for those photons inside your cavity, and you know, how large a particle number could you imagine building up and stabilizing in that system?
So what I would say is, literally the next thing to do is implement the chemical potential. And it turns out it's actually quite surprising. Well, maybe not so surprising. How do we make this chemical potential-like object for the microwave photons? You need to generate some inversion, right? And so it turns out hyperfine Raman pumping essentially gives you the inversion that you need. And so, you know, the next thing to do is make a bigger Laughlin state in this way. I expect we'll be able to do 10 or 20 particles. But there's also sort of an interesting question here, which is, I mean, say you can make it bigger. The real question is, how much of your system is exhibiting any substantial amount of entanglement? How large do you have to get before there's an error, right?
Well, and also more concerning is your stabilization techniques for stabilizing that n-particle state doesn't guarantee you that that degenerate manifold that you've stabilized to, that you can have any coherences in that and maintain them.
I agree completely. And so in some sense, the point is going to be, when you try to braid these things, the whole braiding process has to take place within a stabilization, within the time it takes a single hole to appear and be refilled.
Okay.
And so the numbers look, I would say, fine for demonstrating this physics. Do I view it as a way to make a topologically protected quantum computer? Absolutely not. You know, it's basic science.
Okay.
Yeah.
Yeah, Nai Cheng.
Yeah, could you elaborate a little bit more on how you would be able to study anyon statistics, for instance, from your current experimental approach?
Yeah, so maybe I draw you a picture. There's this really cool idea where if you have a Laughlin puddle, okay, and you can make two defects that bind anyons. Okay, so imagine I put a little dimple here by pushing on the atoms with a laser beam. So I bind an anyon there. Are we okay with that? Okay. And so that'll make my density defect. But then instead of applying a laser beam to put a defect here, what I will do is trap an atom over there. Okay? And the statement is this Rydberg atom that I trap over here will repel all of the other Rydberg electrons in this few-body Laughlin state and bind another anyon here. Okay? But the point is, it's actually bound to this atom, not to a laser potential. So now you can do something really neat, which is actually quite unique to cold atoms. What you do is, you put this atom in a superposition of two different Rydberg states. Okay? And I have two different trapping lasers for the two states. Okay? So one laser color traps one Rydberg state, and the other laser color traps the other Rydberg state. Okay? And now what I can do is take this laser and bring it around in a circle. Okay? And when I come back to where I started, now I do a Ramsey experiment and try to go from this superposition of these two Rydberg states into just one of them. Okay? And the point is that Ramsey experiment is actually sensitive to the statistical phase between these two anyons. Does that make sense?
So that's your plan to...
That's the plan.
So you have to trap a bunch of...
So the question is, how big does the system need to be for this? The numbers, simple numerics seem to indicate a 6 or 7 particle Laughlin state is enough to see the phase. Now, do you see it to 8 digits? No. I mean, look, here they're actually, what are they? I guess they're like semions or something, right? So the phase should be pi. And what people see is in the numerics is like 0.95 pi, 0.98 pi, right? But the point is you can actually see this physics in a real Ramsey interferometry experiment, which I think is pretty cool.
Thank you.
Okay, up there, please. Yeah.
Oh, yeah, so just quick follow-up about the Laughlin wave molecule. So I guess I'm more used to about the electronic Laughlin wave function, which is actually symmetric, but your Laughlin molecules are symmetric. So suppose you can make these many-body Laughlin molecules, and then the entire wave function should be symmetric. What do we still expect the same fractional quantum Hall physics?
So this is an interesting point. This will be the bosonic analog of the Laughlin states, right? And so this relates to this question of what are the statistics of the anyons, what's the charge of the anyons. So generically, if I have a wave function, right, the statistics are 1 over nu, right? And so is the charge. And so the point is that fundamentally, the statistics will be like half a boson, right, or fermion, right, for this nu equals, I guess you do it the other way, right? This is 1 over nu. Yeah, and the statistics are then also 1 over nu, or are nu, yeah, because nu is 1/2. And so and if you go to nu equals 1/4, right, then that becomes a 4th power, and you get half a fermion. But they are still anionic quasiparticles. But I think it's sort of fundamentally an interesting question: which of the properties are sort of the same except for this even versus odd, and which ones are totally different. You can't make, for example, really an integer quantum Hall state with the bosons, because you can put as many photons as you want into each of your orbitals, right? But as long as you have strong interactions, you can do the other one.
Any other questions? Okay, let's thank John for an excellent talk.